What we aim to do in artificial immune systems is to steal or to borrow the computation, whatever type of computation we find the immune system does, and then to copy that computation within a computer system. We go and work with practical immunologists to find out exactly what the human immune system is doing. And the interesting thing about this field is that immunology as a science is also rapidly progressing. So our understanding of the human immune system is evolving in time, and therefore the models that we build of the immune system are also subject to change, which can give us fresh ideas on how to build these immune systems. For example, when the first artificial immune systems were built in the early 1990s, they were based on a principle called the self-non-self principle. Now, this principle assumes that the body can detect any cell or any living entity which is non-self, which doesn't belong to self. Now, this was a really interesting theory and was applied to computer security. However, it emerged in immunology about 10 years later that this theory maybe wasn't as true as what we thought. There was another theory called the danger theory which came along. Modelling the immune system is a really important step in artificial immune systems as it gives us our grounding for the systems that we build. Now, the human immune system is a very complex, very adaptive, very robust natural system, which is what we call decentralised. So unlike the nervous system, which has a brain as a central controller, the human immune system doesn't have this. It's what we call a decentralised system, which has a property called self-organisation. So it has the ability to respond to threats and to repair the body after a threat has been detected and eliminated. And it does this through orchestrating responses through a number of different types of cell. And these cells all work together to aggregately protect the human body from different threats. The immune system is really, really clever because it can remember past encounters with threats. And when it remembers these, it can generate responses really, really quickly the second time. That's what we call the primary and secondary response. And how it does this is through a natural form of optimization where after a protein has first been encountered, the immune system can create molecules which fit that protein exactly. So when it sees that pathogen again in the future, it can respond to it really quickly. So there's an interesting computational property of optimizing something to fit a potential invader. The negative selection algorithm was one of the first artificial immune systems, or AIS algorithms, that was published. You have some form of representation of your data in feature space. And feature space is where you have an n-dimensional hyperspace, which is where you can map attributes from a feature vector, which might look something like this. This is an example of a binary feature with 1, 2, 3, 4 dimensions. For our example of negative selection, imagine we had a dimensionality of 2. And what we do, we initially create a set of what we call detectors to cover this feature space. So we randomly put detectors in our feature space, like so. And what we do is we plot a little region which we class as normal. What we then do in the algorithm is then delete any of the detectors which touch our defined normal region. This leaves us with a tuned population of detectors which only detect things that we have defined as not normal because it's not in our definition of normal. We then take our network data, for example, and we run this system on our network. So we plot these new items, and abnormal data is where you have the anomalies touching the detector within a specified detector radius. So this one here, in fact, all of these detectors, apart from this one, have anomalies in them. These points here do not touch a detector, and these would be classed as normal. For those of you who want the mathematical details, this is often calculated using Euclidean distance. And that's pretty much the negative selection algorithm. So one example of the use of negative selection is within computer security for the analysis of system calls. System calls are the way in which a running program interacts with the computer system and the operating system. And so each running program generates a sequence of system calls. And what we can do with negative selection is we can create our feature vector from a library of different system calls and change the value for each system call to 1 or 0 depending on whether that system call is there or not. And we should be able to find out whether the program is behaving correctly or not through analysing these sequences of system calls. And we can do this by feeding our feature vector of which system calls have been used by that program to negative selection to find out whether that is normal or anomalous for that particular program.
Might that be something like, okay, you found that Notepad is trying to, instead of just save a file, it's trying to do something really cool.
Exactly. So what you can see is whether your programs are behaving as you expected them to, because if not, it might warrant some further investigation. As computer scientists, we're not usually known for our physical demonstrations, as our physics and chemistry counterparts. If this goes horrifically wrong...
And an eye patch, and a big Ghostbusters no symbol through it.